Howdy, y'all. I'm the Don Shaw.
Howdy, my name is Matthew Trevino.
Howdy, my name is Kyle Rex, and our project is going to be the Ball and Beam project. So here's our YouTube link and team folder link. Obviously, our YouTube link isn't up yet, but as soon as this is done, it'll be there. All right, so for our project, we focused on, like I said in the title, a ball and beam. So basically, the premise of this is a ball is placed on a beam, and that beam can tilt, allowing the ball to roll along the beam. And so that gives the ball a, degree of 1 degree of freedom along that beam. And then for the beam itself, the beam is connected to a lever arm, which is connected to another lever arm attached to a servo motor, which is going to control the height of the beam. And then the one end of the beam, the other end of the beam is going to be fixed. And so that means that that end of the beam will not move. And so what the servo gear does is it's going to rotate the beam. It's going to rotate by an angle theta, and then that angle adjusts the lever arm and causes the beam to tilt by an angle alpha. So tilting the beam creates a slope that makes the ball roll due to gravity depending on the tilt angle. And so our goal is to design a controller for this system to control the position of the ball along the beam by adjusting theta. And then to the right here, you can see some physical models of what our prototype and simulation will hopefully look like. And as you can see right there, you have the gear with a distance D, which in our case, that distance D is going to be a lever arm. And then, so that lever arm is then rotated a certain degree, theta. And then there's another lever arm connected from the first lever arm to the actual beam itself. And that's what you can see right there, that lever arm and then you have the ball, which is a distance r from the end of the beam, and then the total length of the beam is L. And then you have alpha, which is the angle from the beam to the horizontal. And then also on the right here, you can see a physical demonstration of the ball and beam system that we are going to try to replicate and improve upon with a ping pong ball, servo motor, sensor, arms, and a few other implementations. So for this, our plan of execution is for mechanical specifically, we need to build the ramp, backboard, and motor arms of the system. And then we need to set up the motor and sensors, and we also need to set up the Arduino Uno connections as well. And then so for electrical and computer, their focus is going to be to create Arduino code to control the motor to balance the ball, configure the sensor to work, and then finally debug, connect, and complete the system. And then on the simulation side of things, it's going to be creating an initial simulation to make sure the modeling is feasible. And then with that complete, we're going to focus on creating a final simulation modeling the complete system. And then third, we're going to create an output that shows the change in distance of the ball throughout the simulation.
So the distribution of the work goes as follows. Kyle is gonna first purchase all the materials. That includes the motor, Arduino, the sensor, the 5-volt power supply, the joints, and the cardboard for the prototype, along with some nuts and bolts. And then he is going to create the initial prototype with the cardboard and then start with the motors, so we have a working idea of how everything is gonna be. And then he's gonna help Matthew with the math lab code and the Simulant code. Um, so I am going to work on the programming side of this. I'm gonna make the Arduino code for the prototype and work on the PID system. I'm also 3D designing a ramp and the lever arms to use, and then we'll 3D print those, and then Kyle will set that up. I'm also gonna debug, connect, and complete the system to configure it, and then probably use trial and error to fine tune it so the ball can stay in the given position. And then Matthew, for the most part, is going to work on the Simulink simulation. He's going to try to make the entire model in Simulink so we can get a simulated graph of the position of the ball, and then we can finally compare that to the actual experimental position, vertical position of the ball.
So this slide shows our timeline for our project. So for the simulation, this week, starting on Tuesday the 5th, I'm going to be working on creating the initial Simulink simulation and hopefully have that done by the end of the weekend. And then starting next week, the week of November 11th, I'm going to work on improving the Simulink simulation and creating the final complete Simulink model and simulation by Sunday the 17th. For our second task is the physical model design and assembly. Kyle's going to be working on that. So this week he's been working on purchasing materials that are going to be required for the physical model. And then next week, the week of November 11th, depending on when those materials come in, he's going to assemble the physical model and also work on the MATLAB code to record the position of the ball over time. And we're going to try and have that done by Friday, November 15th. And then for the third task, is going to be data collection and demonstration. Vedant is going to work on creating the code that's going to control the motion or control the motor that's going to control the motor that'll adjust the angle of the beam, which will cause the ball to move along the beam. And then he's also going to collect data from both the Simulink simulation and the physical model and then compare those. And we're going to try and have that done by next weekend, the November 17th. And then once all of that's done, then we will present our project to the professor and teacher assistant, and we're going to do that on Friday, November 22nd. So the expected outcomes of our project, one, we wanted to make sure we can develop a working prototype that is going to balance the ball in the center of the beam. We want the prototype to be able to center the ball at the center in less than 20 seconds. And then we're going to work on the simulation that will model the movement of the ball. And we want the simulation to have less than 25% error from the physical prototype. And as we're working on this project, you want to better understand how to model feedback control in mechanical systems, and also learn how to integrate coding into Simulink simulations to model our simulated model. And then finally, also identify sources of error between our physical prototype and between the Simulink simulation.